So Chebyshev's theorem. What is Chebyshev's theorem? Well, Chebyshev's theorem has to do with where the scores fall relative to the center, or the mean. And what's nice about Chebyshev's theorem is it will work for any set of data. So it could look like a disaster. For example, back when I first started teaching here at Fisher, I always had one senior citizen student, and it was always a female in all of my classes. It wasn't the same person, but she, being the senior citizen woman, would always sit dead center, front of the room, never miss a class, and would ask a lot of questions, which is nothing wrong with. But she would sit there, and she was always like 75 or 80 years old. And I'm not sure why that was, but literally for 2 or 3 years, every single class, I would have someone that was, in their 70s. So if we graphed the ages of my students, we'd have a big blob right around 20. And then it flattens out. And then we have what I like to call our midlife crisis blob, a little blob there. And then we come all the way over here, and I had my senior citizen blob. The midlife crisis thing is not an insult. I've been through like 4 of them already. So, yeah, I had my midlife crisis. I think I have it every 10 years or 5 years or something. They're like little mini ones or something. So we have a blob, a little bump, and another bump. That's not symmetrical. It doesn't have a nice shape to it. It's not a bell, which is what we're eventually going to be looking for in a lot of our data in this class. It doesn't look like a bell. It's just a disaster. Well, Chebyshev's theorem can handle that. So Chebyshev's theorem shows that in any set of scores, or probability distribution, most of the scores are relatively close to the mean. So here's a picture. This is a disaster distribution. It's not symmetrical, it's kind of like bleh, right? And this line here is the mean, which it probably really isn't, but this probably should go way over here quite a bit more. There's got to be some extreme values way over there. But let's say this is the mean. Chebyshev's theorem says this: if I take my standard deviation and subtract 2 of those from the mean, so let's say my standard deviation is 5, so I would subtract 10 from it and add 10 to it. So between here and here, this is 2 standard deviations below the mean to 2 standard deviations above the mean. 75% of the scores, at least, are going to fall between here and here. So, what does that mean? If I just randomly pick one of my students, I have a 75% chance that their age is going to fall between here and here. It says that 89% will fall within 3 standard deviations. 94% will fall within 4 standard deviations, and so on. So all you need to really know about Chebyshev's theorem is this: the percentages relative to the standard deviations. So if I said what percentage of scores are going to fall within 3 standard deviations of the mean of how many of these books they made a mistake in, right? We don't even know what the distribution looks like, but we can look up the percentage of books that are going to have that many errors in it. We just by looking at this table, this small table here. So this is Chebyshev's theorem. All right. This is a typical question for a Chebyshev's theorem problem. You are not responsible for this for me. All I care that you know is the percentages. And you don't even have to memorize them because you can just look them up in your book, right? All right. The next one, which is the empirical rule, this applies to distributions that look like this, that look like a bell. It doesn't have to be exactly like it. This could be a short bell that has long tails, or it could be a really skinny bell that's really tall. But if it looks like you could stick a handle on it and ring it, the empirical rule will work for it. So the empirical rule shows that in any set of scores that is bell-shaped, virtually all scores lie within 3 standard deviations of the mean. So pretty much everything is going to fall between here and here. This is what most of the statistics we're going to be using this semester will require, is our data to be distributed like this. Luckily for us, processes that happen, that produce like that trap, happen, and the random variations in those processes end up looking like this. So where can it come in handy for you? Well, this is where it can come in handy. All right, so let's say you live on campus here at Fisher. And you have you got your dorm, and your dorm's door is over there, and it's a Friday night, and as a typical college student, there's just nothing to do on Friday night at, say, 10 or 11 o'clock. So you decide, because stats is so exciting, that you're going to do some statistics instead. So at 10 o'clock, you sit down, you open your door up, you take a marker, and 10 o'clock, and you sit here, and you watch your door. Every time someone walks by, you put a mark on the board. Because you have nothing else to do, right? Remember, you don't have a bar on campus anymore, so what is there to do? All right, so you keep doing this. And at 11 o'clock, you stop. Oops. So you have 11 people walk by your door. Then the next Friday, you do the same thing. And you do this starting the fall semester for every single Friday until, not the last Friday, but the second to last Friday of the whole fall-spring semester combo. Then you calculate the mean. So let's say the mean, x bar is equal to 10, and your standard deviation is equal to 2. So on average, 10 people walk by with a standard deviation of 2. All right, so let's look at, and you graph it and it looks like a bell. So let's look at that. So this is 10. The empirical rule says 68% of the scores will fall between plus and minus 1 standard deviation. So 10 plus 2 is 12, minus 2 is 8. So between 8 and 12, there's a 68% chance that between 8 and 12 people are going to walk by your door. Well, let's add 4. So it'd be 14, and 10 minus 4 is 6. That's 2 standard deviations. And then last but not least, 6. 3 standard deviations, so minus 6 would be 4 to 16. All right, we're not even going to go there, because 95 is pretty good. So let's have 6 to 14. So you go to your roommate, I'll bet you $100 that this coming Friday, if you sit in this chair and watch that door, that between 6 and 14 people will walk by that door. You will have a 95% chance of winning that bet. This is how quality control works. Now I'm going to give you just a real brief summary of how this works. It's totally different because it's all computerized most of the time nowadays, but let's go back a few years, and we have a company that's manufacturing marker caps. And there's an assembly line, marker caps are going along, and what happens is someone will come up, they'll randomly select a marker cap, and they take a little caliper and they measure it, and then they put it back on the assembly line, and they go up and they have a chart that has a line down the center with a value, and it's got a line here and a line here. This is 3 standard deviations above and 3 standard deviations below the mean. And they put a little X where that value is. So let's say it fell right here. This is a long sheet of paper with a line down it. Then they do another one. and they put a little X. And they keep doing this. And this represents the random fluctuation that happens in machinery. Well, what happens then, if they measure a little cap and it falls over here, that means something else is going on other than these random fluctuations. The process will be shut down. They'll figure out what's wrong with the machine. They'll fix it. They'll turn it back on again, and they'll keep running it. But everything has some fluctuation in it.